Good afternoon and welcome to the GE HealthCare industry-sponsored lunch symposium at this year's annual meeting of the Organization for Human Brain Mapping. I'm DJ Kwam and I'll be the moderator today, where we'll be talking about SIGNA MR and more to explore. I'm pleased to welcome three distinguished speakers this afternoon, two of whom are my direct colleagues at GE HealthCare, and we have another distinguished guest who will be joining us and giving the primary lecture this afternoon. I'd first like to welcome my colleague Suchi Banerjee. She's the Senior Director for Neurological MR at GE HealthCare, as well as her colleague, as well as mine, Dr. Jaemin Shin, who is another lead scientist in our Neuro-MR division. They'll be speaking to you about new horizons in neuroscience with high-performance systems and AI. I'll first welcome to the stage my colleague Suchi. Thank you.
Hello, everyone. Welcome to the Lunch Symposium. So, as DJ mentioned, I'll start this off today. Thank you. Talking about the new directions we are taking with high-performance systems and artificial intelligence. As many of you know, GE HealthCare spun off in 2023 from General Electric as a leading global medtech, diagnostic, and digital solutions innovator. It comprises of imaging equipments, contrast agents, patient care solutions. We have 4 million imaging equipments in the installed base, servicing over 1 billion patients globally annually. And because we represent MR, this is a quick snapshot of our MR fleet, comprising of 1.5T, 3T, and 7 Tesla. And many of the things I'll be talking of today are future technology in development. So as we look into the future, we see an inflationary environment, depleting helium resources, burnout in radiologists and technologists. We see an increasing burden, socioeconomic burden of neurodegenerative disorders and mental health illness. And at this point, you are thinking, is this a doomsday scenario in a lunch symposium? No, because what we are also seeing is exciting discovery on the pharmaceutical side. We are seeing unprecedented breakthrough in artificial intelligence technologies. So what we are choosing to do is be proactive and shape the future through effortless imaging, through AI and digital workflow. By having sustainable and equitable access in MR. And we are doing that with compact, lightweight scanners that can be deployed everywhere, that have less power consumption and are helium independent, and having full upgradability in our fleet. We are also taking bold bets for groundbreaking discoveries and partnerships that elevate population outcomes with a focus towards oncology, cardiovascular solutions, and neurodegenerative disorders, and expanding clinical indications as mental illness. As some of you might know, GE HealthCare has topped the list of the most FDA-cleared AI-enabled medical devices in 2022, 2023, and 2024, so for 3 years. And we are doing this by delivering effortless workflows and clinical excellence that aims to address low patient throughput and lack of productivity tools, need for repeat scans. Here, often the culprit is motion corruption, which leads to the need for sedation in pediatric subjects and people who are not able to be compliant. Variability in clinical practices that come from variability in the operator, in patient positioning, variability in the clinicians, lack of standardized reporting and workflow tools, and all of these variabilities often lead to ambiguous differential diagnosis that really do not have a favorable impact in the patient's outcome. So we are incorporating intelligence in every stage, from the ordering to scanning to reporting in the clinical workflow. Okay, but if you're like me, you are thinking, this is motherhood and apple pie, all very high level and generalized. So what does this actually mean in the context of neuroimaging? So let us take a look a little bit more into the details. So this is what a rapid push-button quantitative neuroexam looks like. And here you will see I have a combination of things that we have already been putting into product in the past several years and things that we are working towards. For example, in the one-touch scanner workflow, we have patient adaptive coils, AI-enabled landmark identification, and we are working towards adaptive protocoling, implant workflow, and so on. In fast and consistent imaging, we have introduced a deep learning reconstruction, ARICON-DL, which you'll hear more about. We have had in-product solutions, motion correction strategies, such as our 3D perspective motion correction, propeller trajectories that are robust to motion. We are working on, we have introduced methods for consistent diffusion with distortion correction that you'll hear a little bit more about from my colleague. And we are continuing the innovations in vastly undersampled acquisitions with AI-enabled reconstruction, which we are calling Sonic DL, which, for example, in the near future, can give you excellent image quality in a 1 millimeter isotropic 3D T1 scan in 76 seconds. We are also looking a lot into the concept of an image quality dashboard. Today, what we have already is, for example, a real-time data quality check in functional MRI. We have quality assurance tools that look at the drift and the ghosting levels in your scanner. We are advancing them and also developing on the concept of an IQ scorecard. So at the end of the exam, someone can just get a scoring of the exam in terms of mild, medium, or severe motion and a recommendation whether to scan again or not. Parallelly, we are working through our internal developments and with our third parties to develop tools to extract as much information as possible from these images and to have a reporting that is actionable. So I mentioned our deep learning reconstruction technology, ARICON-DL. So this is a technique that was developed to recognize the thermal noise and truncation artifacts in the MR complex data and provide a reconstruction that is more SNR efficient, has sharper, and is sharper. And this has been incredibly well adopted globally, with more than 28 million patients scanned with this technology since its introduction. It is now covering more than 97% of our neuroimaging portfolio, and clinicians across the world have thanked us for increasing diagnostic confidence with this technique. And again, you will hear more about this from my colleague. But it is not just about scan efficiency and consistency. We want to expand the horizons of neuroscience by pushing MR technology to be able to look at things that were not visible before. And so this year, in May 2024, we recently submitted for FDA clearance our head-only high-performance gradient system, SIGNA MR. So what is the SIGNA MR, which is powered by Hyper-G gradients? This is a head-only gradient that can be inserted in a 3T clinical scanner. It has gradient performance of 300 millitesla per meter amplitude, so that's the maximum amplitude it can go to, and 750 Tesla per meter per second, so that's the time it takes to reach that maximum amplitude. So just for benchmarking or comparison with an existing top-end clinical 3T scanner, there the specifications are 80 for maximum amplitude and 200 for slew rate. But high performance does not mean high power consumption. This has the same power consumption of a clinical 3T. Now, how is that possible? That's possible because this gradient coil has a much higher efficiency than the existing gradient coils in clinical scanners. Now, we will talk a little bit more about the advantages of the scanner in exploring the parameter space. We'll talk about the oscillating diffusion encoding and the axonal diameter mapping. But also remember, everything we talked about in terms of the AI tools will also be available on the scanner because of the common software platform. So the initial publication coined this term, this acronym, for mesoscale diffusion with advanced gradients for neuro ultrafast scanning. And as you can imagine, this is a scanner that excels in diffusion imaging. So I want to start by looking at a data set that is not from a fancy acquisition. Many of you here are very familiar with the adolescent brain cognitive development study. It's a longitudinal study that has been going on for 10 years in children 9 to 19 years of age. And this is the protocol for that study. It's multi-shell with a maximum B-value of 3,000. Here I'll draw your attention to two things: the super short T that you can achieve, a T of 40 milliseconds, and look at the quality of the tracks that can be generated from this data. Now let's look at really high B-value diffusions. And as you can see here, because you can achieve much shorter TEs compared to conventional clinical scanners, here you can easily go to a B-value of 30,000 while still having appreciable SNR. Okay, but we don't typically use very high B-values. So what's the advantage of that? I try to think of it as increasing specificity in an image. When we go to those very high B-values, other sources of diffusion are damped, such as the intracellular water movements. And so what you are looking at only is the axonal diffusion. And this can really help one to map the axonal radius or diameter with much more specificity. And that can be relevant in cases such as neurodegenerative disorders or traumatic brain injury, where certain distribution of axons might be preferentially destructed. The other thing that has been a little bit out of the reach for clinical imaging so far is time-dependent diffusion. So we have seen pulse gradient spin echo imaging because these don't need typically a very short diffusion time. But with these longer diffusion times, we are also not able to probe microstructure that is below, say, like 8 or 9 microns. With Magnus, the possibilities for explorations open up because we can achieve the really high oscillating frequencies. We can look at microstructures of the dimensions of 4 to 5 microns, which are much more biologically relevant. So here is a comparison of a clinical scanner and Magnus, just in terms of what oscillating frequency and B-value we can reach for a certain TE. And so here you will see this is for a certain TE. So here in these graphs, you will see for a certain TE, the B-value and the oscillating frequency that you are able to reach. And you can see for the clinical scanner, for 50 hertz, the B-value you're reaching is much lower than what you're seeing here on the right-hand side. Now, what this means clinically is still to be explored and understood. This is one example that has been done by our collaborators at Walter Reed. This is showing here that instead of just looking at ADC or trace, when you look at the ratio of that for different frequencies, you do see different contrast mechanisms. And perhaps that points to pseudoprogression, which is like the holy grail in looking at tumors. It might also help to do a better differentiation of tumor grades. We have also seen some promising research in MS and in traumatic brain injury. And lastly, this is a recent study that was published by our collaborators at Stanford, Jennifer McNabb's group in NeuroImage, that showed for the first time short diffusion kurtosis in the human brain. But it's not just about diffusion, though I started by saying this is a killer diffusion imaging machine. You know that we talked about the really high slew rate, which can help in functional MR as well, in getting shorter TRs and in minimizing distortion and getting very short echo times if you choose to do so. So again, I'll start with something that is not fancy. This is just a 5-minute acquisition of resting state fMRI. No correction done, just showing you the raw TSNR. And I think you can appreciate here the high TSNR. And here I'll show that when we are looking at the default mode network, we are able to synthesize the connection between the amygdala and hippocampus, even though this was just a 5-minute scan. Now, over the recent years, there has been a lot of talk about multi-echo. EPI hyperband is GE's name for multiband. So multi-echo fMRI increases reliability of fMRI data. You are able to take out the physiological noise, and also you gain from the higher improved bold weighting without the dropout in regions of eye susceptibility, as shown here. And you can imagine there is much more flexibility in choosing the scan parameters when you're doing multi-echo fMRI on SIGNA Magnus. Parallelly, our scientists have come up with this really innovative method for silent looping star fMRI. I have been hearing a lot of nice presentations on auditory tasks on language processing. And this method can really help in a different way in MR without the distraction of the gradient switching on and off, to focus on the auditory task, or to do fMRI studies during sleep, or to have a truly resting state fMRI. I won't go into the spin gymnastics of how this works, but this has been demonstrated in several cases for auditory tasks. Also, it enables subjects who feel very anxious for an fMRI experiment to do so, and the results have been shown in various conferences and journal proceedings in collaborations with King's College London, UC San Diego, and so on. So our scientists have now combined silent fMRI with the multi-echo, because now they can on Magnus, with the flexibility of choosing the parameters. And this, again, opens up many more possibilities. So suffice to say, there's more to explore in collaboration with our innovators. And with that, we want to shift gears and talk a little bit more about consistency and longitudinal studies. And for that, I'll hand it over to my colleague, Jae-Min Shin. Thank you.
Welcome, everyone. Today, I will highlight our commitment to improving data fidelity in diffusion and functional MRI. While distortion correction algorithm like FSL top-up, not showing on the figure on the left, but widely adopted in the research setting, but lacking of streamlined console processing limit their clinical adoption. We brought this distortion correction technique in a clinical setting we call progress. First, let's look at how we enhancing resolution without sacrificing image quality. Using our multi-shot diffusion muse with the progress and recondyle technology, we can achieve high-resolution diffusion MRI scan even with the 0.63 millimeter without compromising SNR or increasing distortion. This has been significantly improve our imaging data fidelity. Next, we'll examine deterministic tractography. So you have seen this figure before. With recondyle, we see markedly high sensitivity for delineating white matter pathway related to DBS target, particularly in unsnipped fasciculus, which was previously reported as critical neuropathic pathway. Automated white matter bundle extraction using probabilistic tractography show consistent observation, improving accuracy and reliability when using ERIC and DL. We observe better agreement with ACP-LS, demonstrating more consistent, reliable tractography in unsnipped fasciculus as well as percent minor. Additionally, we see lower uncertainty in fiber orientation, indicating effective noise and Gibbs ringing reduction for both track. Together, high sensitivity, better agreement, and lower uncertainty validate the enhanced quality of our diffusion imaging with the ERIC and DL, further support our commitment to data fidelity. We're proud of collaborating with Dr. Kissing Choi at Mount Sinai on DTI tractography research, further validating clinical significance of this improvement. Data consistency is vital for longitudinal study. Concern about data consistency between software version often discouraging site learning longitudinal study from availing new feature and enhancement like ERIC and DL. To address this, we have investigated data consistency in both functional and diffusion MRI across different software versions in collaboration with our user. No statistically significant difference was observed in comparison between software versions. This is our first necessary step toward addressing concern in discrepancy in fMRI and diffusion MRI measurement between software versions. We are committed to continuing such a data consistency check for every major software upgrade and hardware change, ensuring scanner is up to date without compromising data consistency. Please visit our poster on Wednesday or Thursday. We actively collaborating with research analysis group, including FSL and DCM to NIFTY conversion, MRTrix, and HCP group, ensuring research analysis workflow works seamlessly for GE HealthCare data. We directly answering questions you ask on Eurostar forum and GitHub. As an example, we recently collaborated with FSL and HCP group, ensuring P0 field map processing pipeline works seamlessly for GE HealthCare data. We document this change as well as how-to tutorial on our GitHub page. In conclusion, these advances in diffusion and functional MRI demonstrate our unveiling commitment to improving data fidelity, which is essential for advancing neuroimaging research and clinical practice. Thank you for your attention.
All right, it is now my pleasure to welcome Dr. Ken Weber from Stanford University's School of Medicine and Division of Pain Medicine, where he is a senior research scientist and leader of the Neuromuscular Insight Lab. He will be speaking to us today on his research involving spinal fMRI. Welcome, Dr. Weber.
Thank you, DJ. One moment. There we go. Thank you for the introduction. I'm thrilled and honored to be presenting to you this afternoon regarding our research at Stanford using simultaneous brain spinal cord functional MRI to map sensory and motor function in humans. I have no financial or competing interest to disclose. GE HealthCare is not providing me with any compensation for this talk, and they have not covered any of my costs for being here at OHBM. First, I want to highlight our multidisciplinary team of Stanford collaborators that are directly supporting these efforts. I'm on the application side of this work, and I want to specifically acknowledge Dr. Christine Law. Christine is an MR physicist and co-inventor of the simultaneous brain spinal cord sequence that I'll discuss, and she spends countless evenings keeping our research engine running. Next, I want to acknowledge the U.S. National Institutes of Health for continued support of this work, and I want to acknowledge our collaborations with the Stanford Richard M. Lucas Center for Imaging, the Stanford Pain Management Center, and our growing collaborations with Stanford Neurological Spine Disorders Clinic and the Stanford Orthopedic Spine Center. So the backdrop of this lecture is our interest in spinal conditions, which includes traumatic spinal cord injury, non-traumatic degenerative myelopathy, radiculopathy, and neck and back pain. Spinal conditions are the leading cause of physical disability and pain. We're working towards a future where we can understand the unique characteristics and diversity of each patient to provide them with a diagnosis, an effective treatment, patient-tailored treatment plan, and prognosis, all with a high level of confidence. Unfortunately, we're far from this vision, and I believe this is due to the complexity of spinal conditions and the limited tools available to assess this complexity. The pathophysiology of spinal conditions extends beyond the central nervous system to include the peripheral nervous system, the musculoskeletal system. Injury to the spinal cord or nerve roots disrupts descending motor commands and sensory feedback, leading to weakness, discoordination, impaired mobility, as well as atrophy and muscle compositional changes. Pain, which is a product of the brain, and often a key component of spinal conditions and the chief complaint of patients, is very complex and multifactorial. Several tissues can contribute to the generation of spinal pain, and overall we have low diagnostic certainty of which tissues are the source of a patient's pain. Pain is more than just a sensory input, and multiple biological, psychological, and sociological factors come together to shape an individual's experience of pain. Fortunately, improvements in image acquisition and analysis are making MRI more and more quantitative, and we now have the tools to assess brain, spinal cord, and the musculoskeletal system as not previously possible. And I feel that understanding the interconnectedness of these systems will be key to discovering breakthroughs in the treatment of spinal conditions and will bring us closer to precision medicine in this field. With that backdrop, today I'll focus on our work to non-invasively study the interplay between the brain and spinal cord with simultaneous brain-spinal cord functional MRI to map sensory and motor function in humans. We all know that functional MRI allows for the non-invasive study of neural function with high spatial resolution, provides flexibility in the experimental design, where you can map neural activity evoked during an experimental task. You can also study the brain at more of a network level and assess how different brain regions are communicating with each other. fMRI has really transformed our understanding of the brain in the healthy and diseased states, and it's been key to our modern understanding of the brain's role in spinal pain. Most functional MRI studies have focused understandably and appropriately on the brain. However, the brain is only part of the central nervous system. The spinal cord is a caudal extension of the CNS and has roles in the sensory processing, motor output, sympathetic outflow. And with spinal cord fMRI, the hope is that we can capture and study these spinal processes to gain a deeper insight into normal spinal pathology, diseases afflicting the cord, and mechanisms of treatment. Spinal cord functional MRI, however, has been much slower to develop, largely due to multiple technical challenges. The first major challenge is acquiring high-quality functional images. Spinal cord is small. It's only around the size of your index finger, requiring high spatial resolution, resulting in lower SNR. Next, there's high magnetic field inhomogeneities along the spinal cord due to differences in magnetic susceptibility between the vertebrae and intervertebral discs, leading to signal dropout and distortion with conventional echoplanar imaging. Next, physiological noise is elevated in the spinal cord due to the close proximity to the heart and the lungs, leading to increased cardiac and respiratory noise, in addition to noise from cerebral spinal fluid fluctuations, swallowing, bulk motion of the participant. And finally, there were many analytical challenges with functional MRI of the spinal cord, and the tools that we had were designed for brain imaging, and the field lacked tools specifically for spinal cord functional MRI. So technical innovations over the last 10 to 15 years have significantly improved our ability to assess the spinal cord with functional MRI. This includes improvements in imaging, primarily the application of reduced field of view techniques using outer volume suppression or spatially selective RF excitation pulse, allowing for faster, higher resolution imaging without aliasing. And we can now image the entire cervical enlargement with 1 millimeter in-plane resolution with a TR around 2.5 seconds. We've adapted physiological noise modeling approaches used in brain imaging to the spinal cord, and we commonly also include a CSF regressor to capture additional noise from the imaging time series. With the development and release of open source analysis tools, we now have similar capabilities to brain fMRI, and we can perform region of interest-based analyses, as well as voxel-wise group-level spatial parametric mapping. A major advancement in spinal cord image analysis has been the development and the release of the Spinal Cord Toolbox by Dr. Julian Cohen-Adad's team, which has been a major driver in improving the field's analytical capabilities, and includes functions for pre-processing, spinal cord segmentation, and registration to a standard spinal cord template. The field has also recently come together and worked on harmonizing spinal cord structural imaging, which is used for spatial normalization, calculating gray matter volumes, and assessing white matter microstructure. Multi-vendor protocols are available at spinalcordmri.org. The GE protocol uses product sequences, and with the exception of the focused reduced field of view diffusion sequence, all sequences are standard on GE platforms. And we're currently using this protocol on our GE SIGNA Discovery 750 and Premier 3T scanners. A companion open data set with structural imaging in 260 participants is available for those that may be interested. So these technical advancements are allowing us to map spinal cord activity with greater sensitivity and specificity. In 2016, we were the first to demonstrate robust laterality in a motor task at both the group and subject level. Here, participants performed a left and right-sided wrist flexion task. The group activation level maps are shown, but the left-sided red-yellow blob is spinal cord activity due to left-sided wrist flexion. The right-sided light blue blob is spinal cord activity due to right-sided wrist flexion. The activity extends to the ventral and dorsal aspects of the cord, representing the motor and sensory aspects of the task, with the greatest signal change in the corresponding ventral horn. While these findings are encouraging and demonstrate our ability to assess spinal cord activity, spinal cord fMRI provides an incomplete picture of the central nervous system, and we're motivated to do more. And why was this? That's because voluntary movement requires proper signaling between the brain, spinal cord, and muscle. This includes the descending signals from the brain to the cord to the muscles, as well as the tactile and proprioceptive sensory feedback. And any disruption to any of these areas can lead to impaired motor function. So to fully understand motor control and how these pathways are altered in clinical conditions, we need to be able to assess each site of the neuromuscular system. And this leads to our group's decade-long pursuit of being able to assess the full neuraxis with simultaneous brain-spinal cord functional MRI. To accomplish this, we want to be able to sample the brain and spinal cord within the same TR. As I mentioned, imaging of the cord itself is a significant challenge, with the magnetic susceptibility differences between the spinal cord and surrounding tissues, making T2 star-weighted imaging suffer from signal loss and distortion. So geometric differences between the head, neck, and shoulders also make this inhomogeneity significantly worse. And as you can see from these field maps, there are a few hundred hertz off resonance variation along the brain and spine. So the foremost challenge with imaging the brain and spinal cord together is this B0 inhomogeneity, which is a shimming problem requiring an approach that can adequately shim both the brain and the spinal cord. Our solution to this B0 inhomogeneity is a dynamic per slice shimming, which expands on work by Dr. Jürgen Finsterbusch. We use one set of static second-order shims for both the brain and the spine, but a distinct set of delta F, linear X and Y, and X, Y, and Z shims for each and every axial slice. We also use both axial and sagittal field maps to calculate the amount of off-resonance. Off-resonance varies the most along the spinal cord, affecting delta F in the linear Z shims. And axial feed maps don't provide coarse enough resolution in the Z dimension. Therefore, we collect a high-resolution sagittal field map to calculate the linear Z shim and update delta F for each slice. All the shimming details are published in our 2019 Magnetic Resonance in Medicine paper. I'll just give a short snapshot here. But the first step in the shimming calculation is to calculate the delta F shim, the linear X and Y shims, and second-order shims using the axial field maps. The off-resonance we want to compensate can be approximated by a multiplication between a spatial encoding matrix E and the unknown shim amplitude S. Vector O consists of off-resonance values from the axial field maps. Vector S consists of the shim amplitudes we want to find, with matrix X consisting of the spatial coordinates of the voxels we want to shim. The first three values of vector X include second-order shims that cover both the brain and spinal cord. The next three values are the linear X, Y, and delta F shims for the first slice. The next three values correspond to the second slice, and so on. Finally, shim amplitude S is computed by least squares. One thing I'm not showing here is that setting constraints for the second order shims. In our scanner, we need to constrain the current to under 4 amps. Now, we can use the sagittal field map to calculate the linear shim and update the delta F shim. So for each slice, we plot the off resonance of values around that slice. We then fit a quadratic curve to it. The slope of the tangent is the linear z shim, which we need to compensate. Finally, we then update. Sorry, I went too fast. Finally, we then update delta F using off resonance, the off resonance obtained at that slice location. And the entire shimming calculation is done via MATLAB executable and takes less than 2 minutes to process. In the red boxes here are example images of the brain and spinal cord, as well as B0 maps using our dynamic per slice shimming. You can see improved image quality and greater B0 homogeneity with the dynamic per slice shimming over conventional shimming. Here are the pulse sequence diagrams for the brain and spinal cord acquisitions. I was not able to update this slide, but the brain RF pulse shown is a sync pulse, but we now use a spectral spatial pulse. We also use a 2D spatial selective reduced field of view RF pulse for the spinal cord. The pulse sequence is written with KS Foundation. We're currently using this approach on our GE Discovery 750 3T scanner and the GE Premier 3T scanner, and we've just updated to 30.1. We obtained 30 slices in the brain with 3.4 by 3.4 in-plane resolution, 5 millimeter slice thickness, providing full brain coverage. We obtained 13 to 15 slices in the spinal cord with 1.25 by 1.25 in-plane resolution and a 4 to 5 millimeter slice thickness. All of this in around 2.5 seconds. Alongside the sequence development, we refined our imaging analysis pipeline, which includes cardiac and respiratory noise removal, motion correction, CSF noise removal, slice timing correction, spatial normalization to the PAM50 template, spatial smoothing, and temporal filtering. We're happy to share our analysis scripts, and we're working on packing these up and making them openly available on GitHub. So we first assessed the feasibility of our simultaneous brain spinal cord fMRI sequence and analysis pipeline in healthy volunteers performing a bilateral fist clenching task. You'll see bilateral motor activation as well as bilateral ventral horn activity in the spinal cord. We've now expanded on this and recently completed a study aimed at uncovering brain and spinal cord mechanisms of hand motor control. Here in an experiment led by Dr. Valeria Leva, a past postdoctoral fellow and now a principal investigator with the Italian National Institutes of Health, we aim to map the neural correlates of dexterity. So we have participants complete a right-handed finger tapping task at 1 second, or 1 hertz at 3 dexterity levels. The low task was a single finger response. The medium task was a sequential one finger at a time response. The high task was a single finger response, all digits in a random order. And we see increasing activity in brain, motor, and sensory regions at the group and subject level across the task levels, with evidence of increasing bilateral brain activation with task difficulty. In the spinal cord, we're also seeing increased activity across the dexterity levels at the group and subject level, with the activity highly localized to the right ventral and dorsal horns. In a complementary experiment led by Sandrine Bedard, a visiting master's student and current PhD student with Julian Cohen-Haddad, we had the same participants complete a right-handed force matching task at low, medium, and high levels, corresponding to 10%, 20%, and 30% of maximum grip strength. The primary motor cortex and sensory cortices show increasing activity across these tasks, but the spatial extent of the activation and signal change is a little bit more mixed. However, when looking in the spinal cord, we see more evidence of a graded response in the activity, again with the activation localized to the right ventral and dorsal horns. We're investigating this further, but taken together, aspects of motor control between the brain and spinal cord appear to differ between these two tasks. These results will be presented at poster sessions on Wednesday and Thursday. We're currently applying this technique in degenerative cervical myelopathy, which is the most common form of spinal cord injury in adults. It can lead to hand weakness, to diminished dexterity, difficulty walking, bowel bladder issues, and pain. We have really poor predictors for surgical response, and these are patients tend to be older, tend to have comorbidities, and you want to reserve surgery for those patients who are going to respond. The primary injury is compression of the spinal cord, but there's evidence through imaging that there's changes in the brain and also changes in the muscle that accompany the injury. So our goal here is that we're going to image the entire neuromuscular system to develop markers of neuromuscular health that track hand function. And we hope that we can better elucidate mechanisms of myelopathy, better grade myelopathy severity, and then predict surgical response. And our hypothesis is that patients with less brain and muscle changes will have better surgical outcomes. To accomplish this, we're collecting a battery of outcomes. We're performing simultaneous brain spinal cord fMRI with finger tapping and force matching tasks as described. We're also collecting surface EMG to simultaneously measure muscle activity during the tasks, and we're performing brain, spinal cord, and forearm structural imaging. This includes the spinal cord consensus protocol I mentioned earlier, and then for the forearm, we're performing fat water imaging using an ideal sequence and the small air coils, as well as diffusion imaging to assess muscle size and composition. Imaging, along with the behavioral measures, are collected at prior to surgery, and then we repeat the behavioral assessments at 1 year and 2 year follow-ups. So we've just begun enrollment at the beginning of the year, and we expect this to take about 2 years to complete. So you'll have to wait until OHBM 2026 for preliminary findings. But we hope that these MRI-based markers of neuromuscular health can improve the diagnosis of myelopathy through an improved mechanistic understanding, which will lead to improved surgical decision-making, more effective treatments, and a step towards precision medicine in spinal conditions. Next, I will pivot to our work mapping sensory function with a focus on pain processing. First, I'll take a moment to summarize the complexity of pain processing, which has spinal and supraspinal components. The experience of pain is an integrative sum of afferent activity that's ultimately modulated by the central nervous system to be perceived as pain by the brain. Nociceptive signals enter the cord, ascend to the thalamus, and then to the cortex where the signals become pain. But there are multiple pathways with interneuronal processing that can happen in the cord. There's projections also to the brainstem and other subcortical region. And fortunately, there's no single pain brain region, and the perception of pain is distributed across multiple brain regions. In addition, there are multiple descending pathways that can facilitate or inhibit nociceptive processing in the cord before these signals even reach the brain. Therefore, there's no one-to-one mapping between nociception, peripheral process, and pain perception, the product of the brain, and so nociception doesn't equal pain perception. So with simultaneous brain spinal cord fMRI, we hope to elucidate the interplay between nociception, interneuronal processing, and pain perception, as well as the changes in these regions that contribute to the development and maintenance of chronic pain. Dr. Dario Pfeiffer, a postdoctoral fellow with our team, is leading a stimulus encoding experiment where we deliver different heat stimuli while capturing pain intensities ratings after each stimulus. We're hoping to use this to elucidate the interplay between nociception and pain perception and develop corticospinal markers of pain severity. You can see brain and spinal cord images where the activity linearly increases with stimulus intensity. We're now modeling pain intensity versus stimulus intensity and begin to disentangle nociception from pain perception. Next, I want to slightly pivot to work in fibromyalgia by Dr. Katie Martucci, who was a postdoc at Stanford and is now faculty at Duke. Fibromyalgia is a condition characterized by widespread pain. Years ago, researchers established that there is abnormal brain processing in pain and fibromyalgia, and that the narrative was that fibromyalgia was really a brain amplification problem. But what about the spinal cord? Katie and I combined forces on a study that was the first to characterize abnormalities of spinal cord activity in fibromyalgia. Then in a second follow-up study, we assessed the effects of opioids on spinal cord activity in fibromyalgia. What we learned is that indeed neural abnormalities in fibromyalgia extend into the spinal cord. Using amplitude of low frequency fluctuations, or ELF, we identified an imbalance in sensory and motor activity in the spinal cord, which correlated with fatigue, a clinical hallmark of fibromyalgia. In a follow-up study, to our surprise, opioids actually made people with fibromyalgia look more like healthy controls than fibromyalgia patients not taking opioids. We had to take care in that messaging, just stating that our findings didn't advocate for taking opioids for fibromyalgia. However, these are intriguing findings that we're now working to replicate and also assess altered brain and spinal cord connectivity with simultaneous brain-spinal cord fMRI. Dr. Merve Captain is a postdoctoral fellow on our team and is leading the work on this network-level analysis and studying interactions between the sensory and motor spinal cord networks and their connectivity to brain regions. On the right, you'll see group-level brain connectivity maps to the dorsal and ventral spinal cord gray matter. Dorsal spinal cord gray matter, which has a sensory role, is connected more to sensory regions. The ventral spinal cord gray matter, which has a motor role, is connected more to motor regions. We're now contrasting how these networks change between rest and during evoked experimental pain, and we're also investigating how the spinal sensory motor imbalance we previously identified in fibromyalgia is represented in the brain. We're finishing data collection next month in 60 participants with fibromyalgia and 60 pain-free healthy controls with multiple experiments related to different aspects of pain processing and pain modulation in fibromyalgia. I'm just going to discuss a subset. But studying the clinical experience with neuroimaging is challenging, and a goal of the field is to develop improved experimental models of clinical pain. We've developed a pneumatic plunger device to deliver controlled pain mechanical stimuli to the thumb, which we're using to look at studying mechanical pain processing. And mechanical hypersensitivity is another clinical hallmark of fibromyalgia, and we hypothesize that experimental mechanical pain may be a better surrogate for clinical pain in fibromyalgia. Here we show activation of pain-related brain regions and left spinal cord dorsal horn activation from a mechanical pain stimulus to the left finger. We expect to see heightened mechanical pain activity in fibromyalgia patients once we have that data. Next, I want to mention another study by Dr. Dario Pfeiffer, who's interested in the effects of exercise and movement on pain. Exercise is known to induce analgesia, and in some form, exercise is recommended treatment for all pain conditions. However, the pain-relieving mechanisms of exercise are not well known. So to understand the brain and spinal cord mechanisms of exercise-induced analgesia, we're having fibromyalgia patients and healthy volunteers do a hand gripping exercise while they receive thermal stimulation to the forearm. These, again, are preliminary findings in a small cohort, but we're seeing decreased pain modulation response in the fibromyalgia patients, a behavioral response, enhanced activation in brain pain sensory areas, decreased activity in brain pain regulation areas, and then more widespread spinal cord activation in fibromyalgia. These results will be presented at posters sessions on Wednesday and Thursday. If you're interested in learning more about what's been done by our group and others, Merve and Dario have recently published a review in the space of human corticospinal neuroimaging. So check that out. Finally, I just want to touch on some current directions around technical innovations and developments that have implications for brain spinal cord functional MRI. So we've just started a 5-year study using spinal cord functional MRI to map the spatial distribution of spinal cord sensory processing. Many of you may be familiar with dermatomal maps, but they provide a one-to-one mapping between the cutaneous sensations and the spinal cord neuroanatomy. And we use them to help identify a level of neurological injury, whether that's respective to a nerve root or a spinal cord segment level. However, dermatomal maps have several limitations, and spinal cord fMRI offers a unique opportunity to expand our understanding of dermatomes in humans. So these are some of the limitations that there's variability between the different dermatomal maps and where the spinal cord, where the dermatomes exist. There's uncertainty in what actual neuroanatomy is being mapped. Is it the nerve root? Is it the dorsal root ganglion, the rootlets, the spinal cord segments? They also assume left-right symmetry, clear borders, no sex differences, and then there's also no information on inter-subject variability. So we're using non-noxious electrocutaneous stimulation of the C6, C7, and C8 dermatomes in 120 healthy volunteers to map sensory representations in the cord and test these hypotheses central to dermatome maps. We're also going to study the effects of injury using cervical radiculopathy or nerve root injury as the model condition. And then we have several technical advancements in this project. We're developing a spatial normalization approach that accounts for spinal cord segment level, a surface EMG motor related noise removal tool, and a research grade head neck receive coil. And we'll be testing using these to test the diagnostic value of this technique in cervical radiculopathy. The findings could have implications for pre-surgical planning, pain management procedures, and other procedures that target specific spinal levels. So we're collaborating with Dr. Julian Cohen-Haddad, Dr. Nabardo Lopez-Rios, with assistance from Dr. Fraser Robb at GE HealthCare, and we're building a research-grade head-neck receive coil for our 3T GE SIGNA Premier scanner. The coil designs will be made openly available. We're also collaborating with the Spinal Cord Toolbox team to fully automate our analysis pipelines. We now have tools for improved extraction of the spinal cord from functional and structural images, which is really the last hurdle to fully automating our analyses. And these tools have been included in the latest Spinal Cord Toolbox release. Shout out, hey, we're looking for postdocs. If you're interested in the space of brain spinal cord functional MRI, please reach out to me, come meet me, email me. We're also looking for a postdoc to help improve image acquisition and optimize our brain spinal cord simultaneous acquisition. And then I'm supporting open science. All of our NIH data sets will be, NIH-funded data sets will be made available. We're also working to make all of our code and analysis available as well. So thank you, and I'm just delighted to answer any questions you have.
All right. We do have time for questions. We're not using any apps or anything, so if you have a question, please raise your hand and ask it loud enough for us to hear up at the stage. But we welcome any questions on any of the topics, including Dr. Weber, Banerjee, or Shin.
Maybe I can ask a quick question.
No, sounds good.
Okay, and thanks for the excellent talk. Spines come in all shapes and sizes, and I was wondering, have you encountered any difficulty with spines that are more curved or kyphotic, and what you're doing to address these?
Yeah, so it's a good question. It's a challenge. I'm working with spines that have increased curvature, and you get some strange partial volume effects if you're not perpendicular to the cord. And one thing we do is work with patient positioning, and if you can have a little bit of flexion, then you can reduce the amount of curvature, which can help with that. We also use oblique acquisition and then try to align as best as well to the cord to limit partial voluming. Yeah. Another part would be to try to use more isotropic voxel resolution. So when you do the warping and spatial normalization, you don't run into the issues that you would with highly anisotropic voxels.
Thank you.
Okay. We have a question here.
Yeah.
Go ahead.
Maybe a quick question for you guys. Just wondering, for analyzing the data in these standards, we always have this issue with the phase encoding direction. And sometimes on spinal cord, if we do not use the shaping protocols, there can be a phase encoding effect on it. And we usually have AP and PAs come together and we try to do a bias correction with it. Does that introduce more artifacts at the level of the spinal cord if we do that kind of correction on it, and maybe a follow-up one can work in on that? Like, have you done similar kind of encoding corrections?
Yeah, we have not applied them, but it's been something we've been interested in looking at, but it's not something that we've included in our processing pipeline. But it's open to look at for sure.
Well, thank you for your attendance and attention this afternoon. We at GE HealthCare, we are not an exhibitor in the booth area, but you can now see the three of us here from GE HealthCare as well as a few others in the audience. If you do have any questions sort of specific to the GE HealthCare topics, We have our contact information here. We'll be attending the meeting throughout the rest of the week in sessions. So if you see us in the hall, feel free to stop us. Otherwise, thank you very much, and we'll see you next year.